Welcome everyone here to our first online presentation of the summer while the club's on summer break. We're really excited to get things off the ground here. Big thanks to Mark Walensky here as well for putting together this topic for us to discuss today. Mark's got an amazing background on all this stuff and some really fun stories. So there's no better person to talk about the subject of grounding than Mark here today. And so with that, Mark, whenever you want to get started there, my friend, I'll go ahead and pass it on over to you.
All right, excellent. Hey, everybody, thanks for joining. I know if we record this, other people will be watching it too. But I I go around and help a lot of people with their towers and trying to figure out problems with the radios and stuff. And the one thing that I have noticed is a lot of them do not have any type of grounding on their radios or on their antennas or towers or whatever. So I figured I'd do this topic. And so I'm going to talk about protection of your radio equipment. I'm also going to talk about hidden issues that people don't think about. And when I've discussed what I'm about to talk about with some of the people that don't have grounds, they're kind of shocked about it. So anyway, I'll give you a little bit of my background, and then we'll have a question and answer. We should be able to get through this in like a half hour, maybe. Um, but it just depends. I'll also I'll be highlighting some things with this little marker here that I want you to know about, or specifically something I want you to show. So let's move on from here. Um, I'm going to talk about static, and I'm going to talk about lightning. And lightning is considered a static discharge. Um, a typical lightning strike can be 300 million volts and 30,000 amps. And that figure kind of boggles my mind, but they're very, very powerful. And static electricity um, can range to thousands or tens of thousands of volts. So, for instance, you'll see in a coming slide, you've all walked across a carpet and picked up static and it had a discharge. And that can be up to 30,000 volts, but it's very, very, very low current. And static shocks are pretty much harmless for humans, not including lightning. We're going to make lightning a separate subject, of course, but they could still damage electronic components. And some of the components could be susceptible to just 10 volts. And I'll explain that in a minute. So let me go over my background a little bit. And Mark could probably be interested. The left picture at the top is actually a computer that I had, an MSI 8080, before the desktops ever came out. The middle picture is a picture of my business office, 1976, when I started getting into computers and peripheral sales. Mainly, I sold floppy disk drives at that point. And on the right is an Altair, which was another known computer before the desktop. So from 76 to 95, I had a business with computers. At the same time, I was working in TV and radio since 1969. And because of that, I was an engineer and I became a technical director at CBS Television and Home Box Office. But I'm going to speak a little bit about antennas based on television and radio. CBS puts out a broadcast signal. They had antennas at the Empire State Building. They have antennas at the World Trade Center. God bless their souls; they're gone. And they had antennas now at the new Trade Center. However, these things are, they're a couple thousand feet in the air or thereabouts, and they're getting hit by lightning all the time. If they lose a transmitter or the antenna, they lose millions of dollars. So they spend hundreds of thousands, if not millions, on lightning protection. So they can be on the air all the time, no matter what, while even they're getting hit by lightning. Not that they can't have damage, but they're on the air all the time. Now, that's my experience in dealing with grounding for commercial type radio and television. Now, the desktop PC in 1982, when IBM came out with the desktop, clones started to appear. And in my business, I used to travel to Taiwan and China and make deals with them to get equipment, bring it back to the US, have it shipped in, and I build it. And one of the people, I supplied these PCs to many famous companies, and some of them still have that equipment in their storeroom. But anyway, long story short, RCA has a satellite facility that used to be in West Windsor, New Jersey, right outside of Princeton. And that's where RCA built all their Comstat satellites. I was selling them a lot of desktop computers. And one day the head engineer came down to my facility to look over how we built them. And he came in, looked it over, he left. All of a sudden, RCA was not ordering computers from me. So I called my contact at RCA, and basically what he said to me was, yeah, everything was good except one item. You had no static protection while you were building them. And this is where I started to learn about grounding for electronics. So it turns out that RCA was giving a symposium to their engineers for 2 days on static because they're building satellites. And if you discharge any static into any of those circuit boards, you might not kill them dead, but you're going to lower their lifespan by up to 80%. So you don't want a satellite in space, and because of a 1,000-volt static charge that you didn't even feel, you don't want to deplete that integrated circuit, which is, by the way, protected from radiation out in space and so on. They have shielding on it to protect it. But if you do a static discharge, instead of that spacecraft lasting 40 years, like 50, like the Voyager, would drop dead in 2 years. Well, the same thing can happen to your radio equipment. So once I took that course from RCA, thank God they let me sit in on it, and then started building again the clones, they started buying again from me. So it was a happy ending. But and a lot of you know that I've been a police officer for 30 years, which had to do with electronics, by the way. But that's a story for another time. So I'm not going to talk about that. But in case the question comes up, yeah, I was a police officer for a long time, but I was in the electronic end of forensics. This is a picture on the right of a AM radio tower. The tower itself is the antenna, because AM frequencies, of course, are, very low. So the tower, the antenna has to be very long, as we know from 80 and 160 meters. But anyway, however, they are very prone to getting hit by lightning. They're giant metal devices that are magnets for lightning hit. And I just want to touch on lightning for a minute here. If you notice on the right side of the left picture, right in here, that's the base of the tower, and that's insulated. In other words, the tower sits on an insulated device, and then the weight sits on top of that device there. Up here is a ball that is welded to the tower, and if it gets a lightning hit, the lightning overloads the electrons and jumps into this other ball. And that ball is, as you can see, grounded. So that's how they discharge lightning. There's a giant ground strap. They have to do something with it. And 90% of the time, it'll discharge the lightning hit from a tower. And I have been not next to, but within 100 yards of these towers when they've been hit, when I worked in radio and television. And it sounds like the Jolly Green Giant took a sledgehammer and slammed that piece of metal.
Question.
It was really quite a hit, but it discharged the ground. The transmitter was fine. I had occasions where those towers got hit and it blew up my transmitter. The worst transmitter blow up, by the way, was from a rat that crawled into the final system and stepped across the high voltage line. But lightning will do damage to it also. Go ahead. Question, Dave?
Yeah. Why is it that the two balls aren't connected?
Well, they can't be connected, or you short the tower to ground.
Okay.
The tower is the actual hot side of the transmitter.
Okay.
So the coax line, the feed line, goes right to that metal structure. So if it was shorted to ground to that, you basically are transmitting, you're shorting your coax together. You know what I'm
Okay.
saying?
I
So
got
you don't
you.
want to do that. The lightning is enough, that voltage, where it's going to jump that air gap. And
Thank
that
you.
air gap is it's engineered to a specific separation. Okay. And I've also seen where they put, instead of balls, they have a device like that and a piece of metal like that with a calculated distance, and the lightning arc will jump across here.
Gotcha. Thank
So,
you.
anyway, um, okay. Static electricity. We're going to get to lightning because I think it's important. But before I do, 99.9% of damage to radios and other equipment is caused by static discharges that are not lightning. Let's put it that way, because they're both considered static. Um, Static electricity builds up on your antennas. It's a very common issue. And certain types of antennas in dry climate and even wet climate, you can get interference, noise, and damage to your equipment. And what I'm showing you, this black circle down here, this was a static discharge. This one isn't my picture, but it was from the internet. This is just a static discharge. And if you notice, it's all black in here. Okay. It shorted it out. So when wind blows over an antenna, it can cause a static charge buildup. Snow and dust can also contribute to static. So if you walk on a carpet, we've all had the experience of walking on a carpet or rubbing a balloon, in your hair, if you have hair, and, you put it up on the wall and it stays there. And the wind blowing across an antenna is a phenomenon called triboelectric effect. And basically what that means is, it's a contact electrification. So when two different materials touch, like the soles of your shoe and a carpet or anything else, we've all learned that every time you touch something, you're leaving something and you're taking something. And if you guys have ever had a coffee table, and this has happened to me for years, you have a coffee table and you have young kids when they were younger, and they come in and they put their foot on the bottom shelf of that coffee table, and you tell them not to, but they do it because you're not around all the time. Well, a year or two later, you'll notice that all of a sudden there's a wear mark in that area. And the first 100 times they did it, you couldn't see any wear marks. But static, the triboelectric effect is like that wearing factor. If you touch something and keep touching it, even if it took 1,000 years, you're going to wear it. Well, the triboelectric effect, you're leaving something and you're building up static and you're exchanging electrons. So you walk on a carpet, you get a shock. And by the way, that shock can be up to 35,000 volts. So what triboelectric effect does, it causes a receiver desensitization, potential damage to your equipment. That's what we want to talk about, and interference. Now, just this past week, all my equipment is grounded that has to do with my network, my computer network, computers, and my radio gear. I forgot to ground two things. One was an Ethernet distribution box out in my garage, and the other one was my ham clock. I didn't put them through any type of protection, like electrical protection or whatever. Well, we had a storm the other day, and my Ethernet, thank goodness for Mark, he loaned me an Ethernet distribution switch until I got a new one. Anyway, I blew out the ham clock and I blew out the Ethernet. And when I say blown, it wasn't exploded like a lightning hit, but it was static discharge that doomed them. So you guys, everybody has to think of their system and how to get rid of or prevent static. So I already gave you the example of the balloon rubbing on your hair, and they acquire opposite charges due to the transfer of electrons. So when two dissimilar objects come into contact, they transfer from one material to the other. So that's how static builds up. So let's talk about antenna types real quick. And I'm going through this pretty quick. So, we're probably halfway done. A vertical antenna. Vertical antennas are not directly grounded to earth. but that makes them very prone to static buildup from wind and precipitation. Don't forget, wind contains dust particles, kind of pieces, little tiny microscopic pieces of soil blowing around. So wind is not just wind, it contains a lot of stuff. So the static discharge with a spark could cause noise in your system. And we've all heard, if there's, when you're listening to especially HF, all of a sudden you hear a little crackle in it because there's some kind of a discharge in the atmosphere your receiver picks up. Well, that kind of noise can be amplified if you don't have proper grounding to your equipment. Telescoping antennas are particularly vulnerable to static. There's not much we can do about it. We have handy walkie-talkies we carry around, and most of them have this insulation on, this rubber insulation, and it kind of knocks down the possible static they can pick up. But be aware, they're still prone to taking a discharge and doing damage. Dipoles are the least susceptible than any other antenna to acquiring a static charge. However, they can still pick up a static charge, and we're going to get to how to prevent that static charge in a moment. Some people use loop antennas. If they're not properly grounded, you can also have discharges into your equipment. Okay, so properly grounding an antenna system, including the feed line and possibly the antenna itself, provides a path for that static to dissipate or build up minimally. And the proper grounding of ham radio antennas is crucial for safety also. So you want to protect the operator and your equipment. I can't stress enough the equipment, and I'm going to show you something as we get towards the end about equipment damage that happened to me here in 2020. Okay, we ground an antenna because of safety. We just talked about that. We want to protect against lightning strikes. If you notice, I have a maybe in there because a direct hit by lightning is going to give you damage. And again, we'll get into the lightning strike a little later. But you want to prevent this damage to your equipment. A good ground improves your signal quality, and that's an important issue. And grounding helps dissipate static electricity. So a lot of you have masts. Some of them are fiberglass and so on. As you know, I have a tower, and I did ground the mast to the tower, which is grounded to the ground. And I'm going to have a diagram of that. But what I wanted to show you, this stuff, I use this stuff a lot. SS30, what it is, it's a copper base, because when you open it, it looks like liquid copper, and it's kind of pasty. When I take this wire over here and I want to put a lug on the end of it, I have a compression tool. Inside the lug, I put a little bit of this. And number one, it prevents erosion. Number two, it makes sure there's good conduction between the terminal and the wire. But I use minimum of 10 gauge, but most of my big grounding systems are 3/0 wire that you see there on the left. What I did with my antenna mast, this is the thrust bearing on the top of my tower. Okay, and right in that area where I just circled is where it mounts to the tower. I have a ground lug on that, and that ground lug through a 3/0 wire jumps to the mast and is bolted into the mast. And that is there just to make sure that the mast has a good ground to the tower, and my tower is grounded to a system that I'll show you in a second here. Okay, grounding radio equipment is the same grounding point to minimize potential differences. What I mean by that is you don't run a ground from one radio to another and then from that radio to ground. Every radio, every device you ground should have its own ground to the ground contact area. You don't want a daisy chain is what I'm saying, grounds. You want to make sure each one is individually to the point of the common area where you're going to attach to your grounding rods that are in the ground. So grounding rods, generally grounding rods, like if you go to Home Depot, are 1/2 inch and 5/8. I highly recommend 5/8 inch ground rod. I drive them 7.5 feet in, except around the tower, they're actually ground driven in about 6 inches underground. But I drive them about 7.5 feet, and that's where my common point of attachment is. If I have more than one ground rod, they are interconnected with 3/0 gauge copper. This is a diagram, a rough diagram of my tower. So what I have here is I have a ring in orange. That orange ring are ground rods around the tower, separated by about. The rule is if you have 8-foot ground rods, you shouldn't put a ground rod closer than 8 feet to the next ground rod. So every 8 feet, I have a ground rod around the perimeter of the tower, and then my antenna coax comes down, and what these lines are right here are grounds on that coax, which I'm going to actually show you the ground in a moment. And then they run through ground to the entrance box to my house, and then that box then has a ground on it to earth. So all these grounds are the same ground. You don't want to put a ground in here into the house and it's not attached to these grounds, because what you're worried about is if they're not all grounded together, number one, there's strength in numbers because you can dissipate a larger static charge easier. But the one thing you don't want to do, it can create a voltage difference. In other words, grounds aren't all the same based on soil, based on material. There's a lot of things. So you want all the grounds tied together, including bonding it to the ground, the electrical ground from your electrical box. This is on the left side. You can see the green wires there. That's the base of my tower. So every leg of the tower runs to that circular ground that's around the tower. On this side, and I'll show you a bigger picture down the road here. What you have here is, this is all my my 4 coax coming down from the antennas. They are grounded separately. I should say the coax is grounded by a special connector, and then that ties into the grounds underground. So this is a close-up of what that grounding looks like. So there are several ways to ground your coax right before they come in your house. This is one of them. So it requires that you strip a little piece of coax, and this metal tab is designed for different size. You can get one for LMR 400, RG58, whatever you want. You put the metal tab around it, you tighten the screws down as in slide 3, and then that might look familiar from the previous slide. That's all my grounds, of course, are waterproofed. So I have 4 of these big bulky things tied together in that previous slide. So I just have them bundled together here, and they all go to a common ground. Now, on the entranceway to your house, and again, this is the way I did it. You don't have to do it this way, but you need to have some kind of grounding on all your equipment. So I just spoke to, I think it was Mike Schofield, and he's going to be getting these, which is what I have. These are the Alpha Delta lightning arresters. And on the bottom here, you'll see I have them mounted on a copper plate, where even though the antenna grounds are grounded at the tower, along a ground wire goes underground and attaches to this copper plate. So the ground wire is all attached to this copper plate, and I use this copper plate also with another line on it that goes into the house. And that's how I ground the radio equipment. So they're all commonly grounded. But anyway, these Alpha Deltas have these little screw-in inserts here, and they're filled with a gas that is formulated so that above a certain voltage, it shorts. In other words, it won't conduct, it won't short anything out while things are normal. But if you get a static discharge or a lightning hit, it's going to be above the reference point of this little insert, which you can see on the left picture. You can see it on top screwed in. It's that little brass right there. But anyway, they're replaceable. So if you take a hit or something's not working, you can replace them. They're only like $15 each. But anyway, it'll short above a certain voltage, and of course, it'll short to ground because there's a lug that ties in the back of it to that copper plate. And so if you get a discharge, it's going to short to ground. It's not going to go to your equipment. If it does, it'll be so minimal it won't hurt anything. The other thing I want to mention is this device over here that you can barely see. I have a rotor wire that's buried underground and goes up to the tower. Well, how do you protect a rotor? Well, you can spend $180 and buy a box that you attach your rotor wires to. Or I looked at the schematic of how those boxes are made professionally. And basically, they use what's called moves. And on this picture right over here, you could see a little blue device that looks like a capacitor. That's called a move. And basically, you can get them in different voltages. So I homemade my own, which cost me $15, not $180. But I took a terminal block. I put all my rotor lines to it. And they're not broken, by the way. The rotor lines are just looped around the terminal. One end goes to a move, one end of the move, and the other end goes to ground. Those are 35-volt moves, which is what's recommended for a rotor. And if there's a static discharge, it's more than 35 volts. It's going to short the move, and the move's going to take it to ground, so your radio is protected. So the ground rod's in the ground 7.5 feet in my case. This middle picture is the kit for grounding of the coax. The left picture is, again, the picture of the copper that I use to make sure there's no corrosion where it's bolted and where I put a lug on the end of the cable. This right picture is actually how I have the box set up coming into my house. It's got 2 lighting arresters. And also, if you have Ethernet, which I do, I have 2 Ethernet lines coming in the house. They make Ethernet like static arresters. I keep saying lightning. I'm going to call them static arresters because there's not a lot of protection from lightning unless you spend $1 million. So these are all things that you can do. And on the back of my, where my shack is set up, I have a ground plate, and this ground plate is copper. And a poor man's ground plate is a piece of 1/2-inch copper pipe, and you can hammer it flat and drill holes in it like you see here, and then you can ground everything. But every one of those straps, copper straps you see there, goes to a piece of equipment in my shack. I know it doesn't look very neat there, but that's just the matter. My shack is right up against the wall because I'm in the sunroom of my house. So I couldn't get in there and make them as neat as I wanted. But the point is they're grounded. I have 13 grounds on there for 13 pieces of equipment. Everything is grounded, and every piece of equipment is direct grounded to that block. That block has 3 3AWG copper stranded cable, and that goes to the outside box with a ground rod, and that ground rod is common to all the other ground rods. So I'm trying to minimize static, and I really have not had a problem with static since I have all this grounding done to the system. So I just want to reiterate, proper grounding is essential for draining electricity, and lightning can also cause significant damage to antennas and equipment. And it's important to attempt to have some lightning protection. The one thing that's important to note about lightning as I talk about this, lightning can strike from 10 miles away. So if there's a thunderstorm 10 miles away and it's sunny and not a cloud in the sky where I am, which happens a lot down the shore here, you could still get hit by lightning, both you, your equipment, and your buildings. So even if the sky is clear, if there's lightning within 10 miles, you should take precautions about being outside. You probably shouldn't be cutting the lawn and all that. So I want to talk about lightning a little bit, um, just to prove a point here. On August 6th, 2020, I was in my master bedroom. My wife was in the dining room, which is 15 feet from the kitchen. We heard a crack that I'm familiar with, and I knew that lightning had hit something on our property. I wasn't sure what at the time. At the same time, that crack hit, and I knew it was lightning. My wife let out a scream. And what happened was, of everything that blew in the house, which I'll get to in a minute, we had nightlight, LED nightlights plugged in each room. She was about 12 feet. I measured it from a nightlight plugged into a wall. And when the lightning hit, whatever it hit, exploded, literally exploded and fragmented the LED nightlights. A piece of it blew right by her head and hit the wall, went right into the sheetrock. So when it comes to lightning, lightning is not a joke in any way, shape, or form. But I just wanted to show you. Now, this is my damage. And in this picture, that red circle, you see a brown spot on that chip. That's not the only damage, but that was from the lightning hit. These are my Ethernet cables. And you can see the one that's circled, how black it is. The other one is burned also, but it just doesn't show on camera the way that one does. That particular shot of that Ethernet connector was hit so bad, it welded to the back of the computer. And I had to literally force it out, which broke the back end of the computer off. But the computer was done anyway. Now, you saw a picture of an Ethernet connector that static discharge charcoaled. So yeah, lightning is a lot worse, but remember, you're trying to protect 99.9% of the time against static. If you don't have grounds, I'm trying to push the importance of putting a ground on your system, which I'd be glad to help you with or give you some guidance on. Anyway, after the hit and my wife was okay, I decided to walk out to the garage to see what went on out there. First thing I did when I opened the door, on the left side, this picture, insulation blown off my wall. Later on, I noticed the right picture. That's my garage door, the bottom of my garage door. Lightning blew out the left panel, the left trim panel, and blew out part of the trim. It didn't hurt the garage door, but you can see it did some damage there. I have cameras all over the property. Every one of them blew out. On the right is a power supply. I don't have to highlight anything. You should be able to see the way it's blown up. And there's the culprit. There's a tree 30 feet behind the back of my garage. The closest part of my garage is 30 feet. And if you look at the left picture, you'll see that light brown streak. And the one on the right has many streaks on it. That pine tree is about 100 feet tall. It was the direct hit by lightning, which then, lightning when it hits a tree, boils all the internal liquid. It could raise that tree's internal temperature for an instant to 1,000 degrees, but it boils off all the liquid and that tree is going to die. It might take years. I have one here hit by lightning. It's 15 years, but it's dying. But anyway, on the right picture, you can see the marks all over the tree if you look close enough. But I also wanted to show you this. This isn't a picture of that tree. This is an internet picture, but when lightning hits a tree, it tries to seek its way down the ground. And if you notice at the bottom, this pattern at the bottom of the tree, okay, that is the lightning trying to find ground, and it's going through the roots of that tree. So that tree gets burned out, boiled up, and then the lightning goes down through the roots into ground because it's trying to neutralize itself. Guess what? That's what happened. I had an investigator come out and check it out for me. 70 feet from where that tree got hit are my underground lines to the garage. The electricity went into the ground and was still high enough to get in there and destroy physically destroy. Actually, I'm going to show you. Hold on. If I can get it to work here. Oop, there we go. Okay. Every computer in my house was blown with physical damage. Every router, every nightlight. And I told you, one just missed my wife. Every flat screen TV, every stereo, every thermostat, and it goes on and on. And by the way, my Wi-Fi routers were literally, the covers were blown off of them in pieces. It took me 6 weeks to fix everything, and it cost $8,000. The good news was I've got USAA, and they paid for everything, including they paid me $15 an hour to do all the work. I ran out that afternoon and bought, I think it was 5 new flat screen TVs because they were all blown out from Walmart. But anyway, they were so busy, USAA. If you remember 2020, there was a giant hurricane hit the Gulf Coast of Texas. I think it hit Houston the worst. It was called Hurricane Hannah. They were so busy, USAA, with dealing with Hurricane Hannah. All they told me to do was, we're busy. Send us an invoice every 3 or 4 days, and we'll give you a check based on that. And based on that, they paid me all $8,000. So, that was the good news, and I got all new stuff. The bad news was it was 6 weeks of a headache that I didn't want. So if you don't think that static won't do that much damage, but what static does is static will deplete the usefulness of your radio over time. And let me just explain that better. If you're not properly grounded and there's constant static discharge in your radio, modern radios have some protection against that on the outputs. However, every time there's a static discharge, something is weakened. A chip inside the radio, a chip inside your computer. So instead of maybe that computer lasting 5 years, it might only last 3. So people with new radios that are working perfectly and don't have grounds, 2-3 years down the road, they're complaining, wow, something wrong with my output. I've got bad hum, blah, blah, blah. It's all those static discharges finally took their toll. And when you send the radio in for repair, you have a very expensive repair bill. You want to protect your radio. Your radios, in general, they should last, your lifetime, especially the new modern ones. They have a lot of protection circuits in them. But every static discharge is going to possibly do some damage. So I want you guys to understand that, and that's why I'm doing this. So if you know anything about Ohm's law, you can read this, but there's a common ground point. You reference 5 volts from zero, from ground. That's not always true. Different materials conduct differently. I've had, when I was building computers, the computer boxes that we were buying to build the clones, they were coated with the material to make them evenly, commonly grounded, and also not to rust or get any kind of oxidation on them. Anyway, I've had chassis where one chassis had more resistance than the other, and therefore that particular clone wouldn't work correctly because the voltages were wrong based on ground. So that's why another reason you want to ground each item in your shack is to make sure there's not a voltage difference that's going to cause damage somewhere. I also talk about it, if you can read this, and especially if it's online, you can come back and read it. But there's in an underground electrical system, theoretically, there's no voltage potential difference between any part of the circle. But I can tell you in real life that's not true. So that's why you ground everything. There are measurable voltages. For instance, soil. Soil can be wet, it can be dry, it can be made of sand, clay, a combination thereof. So every one of those has a different resistance. So when you put a ground rod in the ground by your house and the next one out by your garage, the soil's not necessarily the same, and you might have different ground points. So you want to make sure they're tied together. That's the whole idea. One other thing, whoops, I guess I hit it twice. Just an aerial view of my tower, and that little circle is basically the ground system around the base. So I just want to show kind of an aerial view that about 6 to 8 feet out from around the tower, big circular pattern. Um, there's also some theories on whether you use round wire for grounding, strapping for grounding. Strapping is always better, but for our purposes, using a good heavy ground wire, circular stranded is fine. Also need to talk about for damage to your radio. I think all of you know what SWR is. You don't want an SWR higher than 3 to 1. I mean, I probably wouldn't even transmit if I had that. SWR 1.5 to 1 or less is highly recommended. That's an actual reading on equipment I was testing for somebody. I can't remember, but you'll see those are the frequencies, I believe, of Salisbury repeater and then ORB. And that was the antenna wasn't bad. I mean, 2.2, 2.7 is getting a little high, but we managed to tune it a little better. I think everything turned out to be 1.3 when we were done, but you want your SWR low, and grounding can help that. This is going to be a picture. We're just about done here. This is a picture of, I'm not saying you have to do this. I'm just giving you an example. This is what, from the tower, all these coax lines are coming from my tower, and this line up here is from my house, feeds the house. So that's how I ground everything coming from the tower. You'll notice on the left side of the box, the door has a wire to make sure that it is at the same potential as the box itself. So that yellow wire there comes over and makes sure that this door has the same potential, even though they're bolted at the hinges. I have the lightning arresters on 5 antennas, dipole. I think dipole's in here somewhere. 4 antennas up on the tower, and also the RG6 feed from a TV FM antenna that's up on the tower. You'll also notice that down here, there we go. That circle I'm making, if you could see it, there's 2 little rectangular shaped boxes. Those are the Ethernet feeds that come up to my house, and they go through. That's also a static protection device, possibly lightning protection. And the yellow wires from them are bolted to the copper plate. The copper plate then has up here has a stranded 3 AWG ground wire that goes into my pole barn, and there's a ground bus in there to ground everything too, except I forgot about the ham clock and the Ethernet, and that's what happened. They got static. It wasn't super high voltage, but it was enough to damage them and kill them. So I realized, to me, this is not overkill, this box. To you, it might be overkill. You may have 1 radio, maybe 2, and sure enough, this would be overkill. But I highly recommend, before this coax comes into your house, no matter where it's grounded, that you have lightning protection on it. Now, these things are $50, $60 a piece, but they might save you a $3,000 radio. So keep that stuff in mind. That if you're having a grounding problem, if you want me to come out and look at your grounding and see how it is, I mean, I'm not the expert, but I have a lot more knowledge about it than a lot of people, mainly through RCA's training and my experience in radio and television. So static, keep in mind, is your enemy. That's your biggest enemy, and you want to kill it before it hits your radios, because little by little, it'll whittle them down, and you'll have a problem. Now, hopefully, I've explained it correctly, and everybody understood. But do you guys have any questions?
Man, Mark, I have questions and comments all around, man. First of all, this is really, really fascinating information. Just going back to the beginning of your presentation too, I never knew that AM towers were actually the antenna.
Yeah.
I never even thought about that for some reason. And that ground, those 2 balls, that created that air gap. Again, that was just really, really interesting. I never knew that's how that was handled, but it makes perfect sense. You know, when the tower itself is the driven element, you can't have it connected directly to ground because yeah, it's just like a
Yeah.
short in the coax. So that makes perfect sense.
Yeah.
Um,
Well, let me just interrupt on that note. If you notice those towers, there's usually 3 to 5 of them or more on an AM station. And the reason is, depending on their pattern, creates directional capability. So if there's another station on the same frequency that the FCC thinks about this and goes, hey, 200 miles away, skip at night, you're when the atmosphere cools off, you're going to interfere with it. So we don't want as much signal going in that direction as the other direction. So all those antennas are set up for a pattern, and it could look like a starfish. You know what I'm saying? It's stronger in one area than the other. But yeah, it's fascinating, the AM stuff.
it was
Good.
super cool, super cool. And you know, I was kind of curious. Maybe you could help me explain this a little bit too. And you kind of did help answer this when you were talking about grounding the radio itself. You know, at least just about every radio I've seen, you know, has some kind of grounding lug on it. And I know me personally, I've been kind of operating under the facade that because I'm using a power supply here at home, the power supply is plugged into my wall, which I think is grounded. So is there an issue with that misconception?
Well, your electrical system does have a ground um, out by your box. You could see they hammer a ground rod in there. I protect electrical. I have what they call them. I think they're trip light multi outlet that are not the cheap ones, the really good ones, like the $300 ones. And I all my electric is plugged into there for any of my equipment. But in addition, you still could have a voltage potential um, through the electric current in your house to your radios. So even with your power supplies. So everything I'm telling you, I ground my power supplies. I I also make sure that the grounds for my radio system are also attached to the grounds for the electrical box. So they're all tied together. So we're all, at the same place. So yeah, I would do that if you're not. I wouldn't just trust the grounding in your electrical outlet to make sure that that ground connects to everything else. I would still bond it to your other grounds.
That makes sense, especially when you were describing about static electricity, how the radio itself is still prone to receiving static electricity when you know there's no connection between that and your ground. You know, you're just getting power from your power supply. I guess there's still room for static electricity to affect the radio in some way, I would imagine.
Yeah, it does, and it can also come through the air. It also can be radiated where, if it's strong enough, it doesn't matter if the frequency doesn't match your radio that you're on, doesn't match it. It could still interfere with the radio. We've all heard that. I mean, HF, you can, lightning hit 100 miles away, and you get all that static across the band, solar flares, everything else. So, yeah, it can happen. But you just want to make sure everything starts on the same zero level that we call ground.
Yeah, yeah. You know, one thing I wanted to comment on as well is I loved that little metal tab that that you showed that kind of spliced into your coax. I've never seen that before. Actually, that's a really cool piece of tech. Makes it a lot easier to splice into a
That
piece of
that thing
equipment.
there.
Yeah, that's exactly it.
Yeah.
And
No,
so,
they took a while. I mean, you got to be very. They're not too bad to install. They give you good directions because it's a brand company, but waterproofing is kind of a bitch because there's a lot of work to waterproofing them, but it pays off.
hmm yeah, those are really cool. And so basically, where would you use this? Would this be in line with your coax to the antenna? Like if you were trying to ground something there?
Well, in some ways, you can put it where you want. What I did was, and what was recommended from my experience with towers, at the bottom of the tower is where I put these. So where the coax comes down from the tower near ground, I put all these grounds on, and they were grounded to the loop that's around the tower. Okay. And then I still have, when the coax goes underground and up to the box to the house, I still have the static lines, the alpha deltas or delta alpha, whatever it is, that I use to ground them again to discharge any static that may get through to that point. So I'm protected at least 2 points.
That makes sense then. Yep. So yeah.
Now you can also use, instead of these kits, I mean, you can just have, I mean, you have to waterproof the connector, but you can cut the coax, put a connector on it, and put a metal plate on the ground, a copper plate or whatever. They make them, or you can make one yourself. And then you put a barrel in there, and that barrel is on the ground. That's to the ground rod. And you screw in your PL259, and then you put another connector on and screw another PL259 or an N connector into it. And now you have another path that works just like the picture that's up there, but the picture that's up there is really good. It works even better than that.
Gotcha. That is awesome. And the lightning arresters in general, I loved how you explained how those work. You know, I never really knew how those work. I just thought it was magic in a little box.
Yeah.
Hey, Marshall.
It's an inert gas. It's an inert gas until it reaches a certain voltage, just like the moves, if you're familiar with them. But you know, at some point, it takes that charge and it can't hold it, and it shorts it to what happens to be a ground.
Yeah, 100%. How many of you guys are using lightning arresters right now for your antenna coming into the house? We got Dave over here. Cool. Yeah, Mark was really helpful with me too. I built a very small version of what he's got at his house. I just have 2 antennas, you know, one for my HF and one for my VHF and UHF dual band antenna. They just go right into those lightning arresters. And, you know, I still have some work that I need to do to kind of bridge it all together and make my grounding a little bit more efficient here at home. But I got some bases covered, but I would really like to get to the station grounding next. I think that's my big thing.
All right, guys. I just wanted to. I just wanted to tell you guys, the club, all its associates, and everybody I've met through the club and through ham radio, some of the best and most respectful people I know that I've ever had the pleasure to meet. And God bless all of you, because, you know, there's always somebody out there who knows something I don't. Everybody's respectful, and especially coming from police work, you don't get that a lot. So I just wanted to thank everybody for that.
Mark, thanks for all the incredible support you give all of us.
Yeah, thank you,
man. Oh, I appreciate that. Yeah, I have fun doing it. It's just something I like to do.
So. It's awesome. It is awesome.
Yeah, that was great. I appreciate it.
All right. Well, hopefully I didn't put everybody to sleep. Mike, I see you sleeping. No, just kidding.
Sorry, I'm not in my optimal position. My computer chair broke, and I'm waiting on parts to come in.
I know me.
Yeah, I can. You know, when we start meetings again, I could bring in samples of how that ground you were talking about, Mark, works. We can even put one together, you know, just to show everybody. But they're phenomenal. They are a good ground because they have so much surface area of the braid that it's easier to dissipate. You know, any of the static. Guys, remember one thing. If you don't remember anything else, a direct lightning hit, there ain't going to be much you can do about it. You're going to have damage. But static is 99.9% your enemy. So the static is what you want to make sure is always grounded out. So, and I know I'm working, Jason, with you and your dad. We'll get you straightened out there. Yours is real simple. You're not going to spend a lot of money. So.
Unfortunately, Rick Holloway just had this happen 2 weeks ago. He had a strike to a pine tree in his yard that his 80-meter antenna went across, and it came inside and zapped pretty much everything electronic.
Ouch. Ouch, man. Well, I'll tell you, this definitely has me thinking twice about how my current setup is, and I never knew how much static was more of an enemy too than lightning. You know, you kind of think, well, lightning only hits every once in a while. It'll probably never hit me. But static, everyone can be affected by that. So,
guys, I got to go to an appointment. Thanks again, Mark. Okay.
Yeah, no problem, Dave. All
All
right.
right, see you all
Thank you.
later.
I appreciate it, you guys. I'm ready to wrap up here too. Then, Mark, thank you again. What a wonderful presentation. Anybody else have anything else for Mark before we go ahead and conclude the meeting for today?
Just thanks for doing this.
No,
Mark.
I'm good.
Yeah. Thank you much.
Good.
Awesome.
All right, guys. Have a good one. Thank you.
Yeah, appreciate
All
it,
right,
guys.
see y'all.
Enjoy the
See
weekend,
ya.
everybody. Take care.